So you've written the book called The Idea Space. Now, for all of our listeners out there who are probably saying, "What the hell is an idea space?" Give us a brief little introduction to what is the idea space.
Yeah, another great question. So, an idea space consists of your thoughts, emotions, sensations, and perceptions. So, thoughts includes words, pictures, songs. Emotions includes pleasant, unpleasant, anything in between. Sensations are the classical five sensations, right? And then perception is just the ability to recognize something. So, like I see a mic, I know that's a mic, right? So, those are the elements of consciousness, and those are the elements of an idea space. Another element of an idea space is the null set. So if you're not familiar with the null set, it's just nothing, like nothing at all. So if something is like missing in a table, it's the null set. There's just nothing there. So those are the elements of the idea space, and then there's also an identity to an idea space. And the identity of an idea space is essentially the one thing you'll remember out of an idea space. So if you're listening to this live, right, you're probably kind of like listening to a whole lot of conversation, and then at the end you're going to have a takeaway, right? And what is that takeaway? That's going to be the identity of your idea space. So that's kind of like the fundamental properties of an idea space. But from there, we can get into the more mathematical properties, which are the idea space is uncountable and the idea space has zero measure. So having uncountable is a doozy of a conversation, but the basic way to understand it is to relate it to something else that's uncountable. So according to general relativity, it's the how we measure stuff is based on the real numbers, right? And the essential argument is this, right? Let's say that you have your x-axis is like looking right in front of you, your y-axis is looking to the right, and then your z-axis is looking straight up. Essentially, imagine you have a ruler that's coming out in your x-axis and it just extends for however long you want. And you can make any single measurement that you want, 2.23, 5.68, 0.2342, whatever you want, right? Let's say that you list an infinite amount of them. The whole argument is, and this was developed by a guy named Gregor Cantor in the late 1800s, is that for any for any measurement that you make, I can always pick a measurement that you did not make, right? And the basic gist of it is basically saying you introduce a new number where the first decimal point of that new number is not equal to the first decimal point of your first measurement. Then the second decimal point of that new number you introduce is not equal to the second decimal point of that second measurement that you make. And then you just keep iterating this until infinity. And you get a new number that wasn't in all your infinite amount of measurements. So uncountability and the real numbers being uncountable just means that there's a larger size of infinity, right, with the real numbers than the natural numbers, the rational numbers, and the integers, which are a smaller size of infinity.
So where does the whole premise of the idea space being? I don't think that point has really honed in with me yet. If you want to give that
Yep.
another shot, like where comes the point of the idea space being uncountable?
Definitely.
I'm just trying
Great
to understand
question.
between
So
like uncountable or like, is it countably infinite? Is it countable but like in like, you know what I mean when I say like countably
yeah,
infinite as well, right? They're all like mathematical ways to describe, because countable and uncountable might seem like, oh, they're just words in English, but in math they're like vastly different things. So I just want to ask you, maybe
yes.
hone in on that point a little bit. What makes the idea space uncountable?
Yep. So I'll give the intuitive argument, and then I will go into the math of it because
Let's
I
hear
think
it.
that'll be
Let's
interesting
hear it.
too. So again, the intuitive argument for why space-time is uncountable is because there will always be a measurement that I can make that you did not make. So for the idea space, the argument is that there will always be an idea that is had that wasn't had before. So this can be based on the proposition that each discovery has a new idea or a new question, right? And to give a more concrete example is, let's say you're living in 1680, right? Pre-gravity. And let's say you try to count all the idea spaces of everybody that's living right there. You just get an infinite amount, right? But then in like 1686 or whenever Newton dropped Principia Mathematica, the new idea of gravity came, right? So where was that idea in the infinite list of ideas before, right? It wasn't there. And you can get like the same concept goes with idea spaces, right? Like before you guys heard of an idea space, you had like all these thoughts and you could count all the infinite amount of ideas. And then a new thought comes in, the idea space. Where was that before in the infinite amount of ideas? It wasn't there. So that's kind of like the intuitive approach. For a more mathematical approach, like what does it mean to count, right? So in order to count something, there has to be a bijection between the natural numbers and whatever set you're counting. So again, the natural numbers are just 1, 2, 3, 4, 5, so on and so forth. What is a bijection? A bijection is an injection and surjection. And what are those two words? Mathematicians have the best language.
I love this.
So an injection is basically a one-to-one function. So for every A, there is exactly one B. But not the whole domain of A doesn't have to go to the whole domain of B. So for example, if you have 4A and 5B, just every A has to go to 1B exactly once. That's onto. That's one-to-one. Something that is surjective or onto is all of A maps to all of B, right? And a bijection is something that is one-to-one and onto. So that's basically, if there's 5 elements, imagine you have 3 dogs and 3 cats, right? And the first dog maps to the first cat, the second dog maps to the second cat, and so on, right? And you have a bijection. There's a one-to-one relationship that maps both the whole domain and range. Mm-hmm. And when you count something, the thing that's interesting is that if there's a bijection, then there's the equal amount of elements, right? If there's a one-to-one relationship that is onto, then they'll have the same amount of dogs as there are cats, right? So bringing this all together, something is countable if there's a bijection between the natural numbers and what you want to count. So what you're essentially saying is that the idea space is uncountable because there is no bijection between the natural numbers and the amount of ideas. Because if we did it like the same example that we looked at, like in 1680, we count all the different ideas, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Where was gravity in that? It wasn't there. So there's no bijection between the natural numbers and the idea space, and therefore it's uncountable.